This is Mr. Keppel, and welcome to PHYZR number 4, What is Motion? This is page number 1 from the motion unit. We are finally ready to start physics. We're done with all the preliminaries, and now it's time to move on to actual physics. Now, if you remember, the definition of physics is the study of matter and its motion through space and time. And so clearly, motion is one of the most important concepts underlying physics. And so the purpose of today's PHYZR is to basically start to get you to think about what is motion, what precisely is it, and what are some of the physical quantities that we measure in order to understand and describe the motion of an object. I want to begin with this clip. This is a time-lapse video taken from downtown Los Angeles. I'll put a link to the full video in the description. What I'd like you to do is to watch this video. I'll just let it loop for a while here. I want you to watch this video, and on your paper I want you to write down some examples of motion that you see in this video. So for example, the cars are driving past on the freeway. You wouldn't want to just write cars, because cars aren't an example of motion. What if the car is not moving? So you need to say an action. You need to have a verb in the sentence that you write down. So remember what I just said, cars drive past on the freeway. So just take a moment to watch this video. I'll leave it up here let it repeat for a couple minutes. And I want you to try to find as many examples of motion as you can and write them down on your paper. I'll take you through a few of the most common ones that students mention. The first is they mention the elevator here. Just wait for it. There it goes. The elevator is moving up and down the side of the building. There's also trees blowing in the wind. If you look back here, you can see that there's a cloud that just passed by. Let's wait to see if we can see it again. There it goes. You can also see an airplane fly by there. Just missed it right there. And when the video repeats right here, you see another airplane pass by there. So airplanes are passing by overhead. Clouds are passing by overhead. Also, if you notice in the sky, if you just watch the color of the sky, you'll notice that it goes from being light at the beginning of the video, and it slowly starts to darken. So what motion is that an example of? What's moving that causes the sky to dim like that? And that's right, it's the Earth. The Earth is spinning. The Earth spins. Motion is all around us, you guys. It's everywhere you can look, everywhere you can think of. What I want you to do now is to imagine a universe without motion. I want you to describe what it would be like to live in that universe. You can write it down on your paper, or you can just think about it. What would it be like to live in a universe without motion? When we did this lesson in class last week, this led to a very long, very rich classroom discussion. And I'll just highlight a few of the things we talked about, see if you thought about these. The first thing most people say is that we would die. That if nothing could move, then we wouldn't be able to breathe, our heart wouldn't be able to beat, and we would die. And I actually say that's not true. Because if a universe didn't allow anything to move, then you wouldn't need to breathe. You wouldn't need your heart to beat, because you wouldn't be using any energy. You wouldn't be moving around. Your body would have no need to replenish its energy to sustain your life. You would just stay the way you are. Every single atom, every single cell in your body would just stay the way it is. And if you take this to another step, it means that in a world without motion, you would live forever. Your cells wouldn't be able to die. The actual physical process of dying requires the movement of your cells in order for them to die. So a universe without motion, you would live forever. But it wouldn't be much of a life if you weren't able to move and to do things that you enjoy doing. You would basically be frozen. And that's not a very fun life to live. The next thing most students start to realize is, oh, wait a second, if nothing can move, then that means that we can't see anything, because light is how we see, and if light travels at a certain speed, in a universe without motion, light wouldn't be able to go anywhere. It would be stuck in place, and the world would just look black. You wouldn't be able to see anything. And even further, taking that to the next step is your brain wouldn't even be able to process the information that it would be able to see anyway. You wouldn't even be able to think because your thoughts are formed by moving neurons in your brain and firing electrical impulses that send through your nervous system. You wouldn't be able to feel, think, or hear anything. It would basically be the most boring place ever. And eventually, finally, some of the smartest students realized that without motion, there wouldn't even be a universe. When the universe first started expanding out after the Big Bang, that wouldn't have been possible. You would not be here were it not for motion. So realize that motion is the most fundamental characteristic of our universe. And as physicists, we need to understand what motion is. We need to be able to describe motion. And that's going to be actually our goal in this class for at least the next 3 months, is we're going to be studying everything there is to do with motion. So let's begin by talking about objects that are motionless. How could we describe a motionless object? Well, as we just said, in a universe without motion, every object would remain in the same position forever. Every cell in your body, every atom in your body, every molecule of air in the air that you breathe, it would all stay at rest. And that's what we say when an object is not moving. We say that it is at rest. So this is the most basic concept of moving, is to describe an object that is not moving, we say it's at rest. So when an object is not moving, it's said to be at rest. And a lot of students, when they hear this, they think, isn't that one of those laws? An object at rest stays at rest? And it is. That's part of Newton's first law, which we will be discussing in our next chapter when we start to discuss Newton's laws of motion. But for now, just realize that if you hear the word rest, that means speed equals 0. Motion is not happening. The object is at rest. It is not moving. It's in the same position. One of the first questions we can ask ourselves in order to understand the motion of an object is to ask, where is it? Because if you ask this question and the location of the object has changed, then you know the object is moving. So before we can establish whether something is moving, we need to first understand where it's located, and that quantity is called position. Now this is a physical quantity, so we're going to write down position, and we're going to write down the symbol for position, which is lowercase x. The definition of position is a measurement of the location of an object at a point in space. That's where the object is located. And it's a measurement because position is a physical quantity, any characteristic of an object that can be measured. Realize I've given you the symbol x, the definition, and finally there's one last thing we give for every physical quantity, and that is the unit of measure. The standard unit is the meter, and it's abbreviated with the lowercase m. Let's try to understand a little bit more about what position is. I want you to look at this picture. This is Miss Wu. She's on the 3rd floor at Fremont High School in the main building. Miss Wu used to teach chemistry at Fremont, but she's moved on to bigger and better things. So the question is, what is Miss Wu's position? Now, please realize that when you give me the measurement of her position, you must give it to me with the unit meter. So take a moment, look at this video. Actually, this isn't a video. Look at this still image that was taken from a video. We'll see the video next lesson. And I want to know, what is Miss Wu's position? This is not an easy question to answer. I've heard a lot of answers from students. Many students just say, I don't know. Actually, most students just say, I don't know. A few students say, she's about 2 meters away from the lockers. Other students say, she's about 10 meters away from the stairwell. And the best answer I've ever heard any student ever say was a student said that she's about 2 meters in front of the camera that took the photograph. I actually like that last one a lot. I think that's probably the best answer I've ever heard to say what her position is, because you realize here that saying the position of an object is not an easy thing. And in fact, we need to decide at an origin, a place that we're measuring from. So some students chose the lockers. This other student chose the camera that took this picture. We need to have a 0 point. So let's go ahead and define the 0 point to be here on the left where that dotted pink line is. And now I'll ask you the question again, what is Miss Wu's position? Those numbers on the bottom are marking out meters from that 0 point. So what is Miss Wu's position now? It should be a lot easier to tell. The last thing that can be kind of confusing is, where are we measuring from? Are we measuring from her leftmost arm, her rightmost arm, from her foot? Where are we going to measure her position? Notice she's spanning about a meter from 2 to 3. Her body is spanning across that. Are we going to say Miss Wu's position is between 2 and 3 meters, or is there some better way to do it? And typically the way we do it is we define an object as a dot, as a point particle, and we say that the point particle is at the object's center of mass. So I've drawn a line here through Miss Wu's center of mass. And so her position would be x equals 2.5 meters. We can see that she is standing 2.5 meters away from the origin. And as you can see, this means that position is a distance. This distance that she's standing away from the origin, that is her position. Position is a distance, and that's why we use x for position, even though x typically means distance. We can actually rewrite our definition for position as a measurement of the distance from the object to the origin. So this definition more clearly specifies that position is indeed a distance, which is why we use the unit meters to measure the position of an object. Here we'll play the video of Miss Wu walking across the hallway. She's no longer standing in the center of the hallway, she's now walking across the hallway. Notice I've provided a timer down here ticking off the seconds as she walks across the hallway with these meters down below. What I want you to realize by watching this video is that her position is not the same. She is not at rest. Notice that as time passes, her position is changing. So we can see that position and time are connected. In fact, the physics of motion is the study of how the position of an object changes as time passes. The goal of any physics problem, as it relates to understanding the motion of an object, the goal is to determine the position of the object at every possible time. And you can see that a video is a really good way of doing this, because the video actually, if I go frame by frame in this video, it can actually show you her position at each of these small incremental positions of time and space. So you can see that if I asked you, where's Miss Wu at 4 seconds, then now she was at 4 seconds, a little bit past 3 meters. Let's watch it again. So at 4 seconds, now she's a little bit past 3 meters. So the physics of motion is the study of how the position of an object changes as time passes. In fact, we say that position is a function of time, that we will have an equation that will have x, position, is equal to something time. And that'll come up in a later lesson. So position depends on time. If I give you a time, for instance, 2 seconds, where's Miss Wu at 2 seconds? Well, she has a specific position at 2 seconds. She can't have 2 different positions at the same time. She's not going to, split her body in 2 and be at 2 different positions at once. An object will only occupy 1 position at one time. which is why position is a function of time. It has to pass what's called the vertical line test for functions. So we just noticed that when a position of an object changes, the object is in motion. So realize that this concept of change is one of the most important concepts, not just in physics, but in all of science. And it's such an important concept that we give it its own symbol. So in physics, the Greek letter delta, that's a triangle, but it's actually the Greek letter delta, which is capital D in the Greek alphabet. So the Greek letter delta is used to represent a change. So the way we use this symbol is you can write delta, any symbol for a physical quantity, and it represents the change in that physical quantity. So for example, delta x would be the change in position. Delta t would be the change in time. So what would delta m signify? Realize that m is a symbol, not a unit abbreviation. This is not change in meters, this is change in mass. Symbols are representative of physical quantities, not units. Units get abbreviations and they always come after a number. And delta v would be the change in speed. So make sure you understand this. The symbol delta is used often in physics, and you're going to have to get quite familiar with it. Notice that we're writing two symbols to represent one concept. Delta x, change in position. Delta t, change in time. This isn't two separate variables, this is one variable. The next question we can ask is, how far has an object moved? From its initial time to its final time, what distance did the object travel through? And this physical quantity is called displacement, and it's symbolized delta x, because as you can see, if an object is moving, then its position changes, and a measurement of its change in position is called displacement. Displacement is the distance from an object's initial position to its final position. So for this baseball player, you can see his initial position was at a home plate. His final position was over here. Actually, probably made it to first base, but this picture doesn't go that far. So we'd say the displacement is the distance traveled from the initial position to the final position. It's this distance here that signifies a displacement. And of course, since it's a distance, the unit is the meter, abbreviated with lowercase m. Let's look back at the video of Miss Wu. And now we're going to start this video at 1.835 seconds, or approximately 2 seconds. And notice her position is at 1 meter. This is her initial position. And as she walks, there's her final position. Her final position is about here. And notice what time her final position is. Let's make sure you understand this definition. Displacement is the distance from an object's initial position to its final position. So in this video, that's a repeating of Miss Wu walking. What is her displacement? Often I have a lot of students that say 3, that she's at 3 meters. But realize that is not her displacement. That's her final position. Because realize that she started at 1 and she ended at 3. The initial position is the first position. The final position is the last position. And you can see that the displacement is the distance between these two positions. So she actually has traveled a distance of 2 meters, moving from 1 to 3 meters in her position is a change of 2 meters. We can write this mathematically using these symbols. We'll use x sub 0, or as it's often referred to as x naught. That's N-A-U-G-H-T, x naught. That's the initial position. So x naught, the initial position. We'll use x for the final position and delta x for the displacement. And there's a mathematical formula that relates these together, and it's delta x equals x minus x naught. Now we'll go ahead and plug in here to this formula. So we know what her x is. The x was 3, so we'll plug that in for x in the formula. We also know what her initial position was. It was 1, so we'll plug that into the formula. And the formula says to subtract these two measurements, and we have the displacement. So the displacement is 2 meters. And the last question we're going to talk about today is, how fast is it? How fast is Miss Wu? In other words, how quickly is her position changing? We know she's moving because her position is changing, but how fast is the position changing? And that quantity is called speed, and the symbol for speed is a lowercase v. The definition of speed is the rate at which position changes. Rate means how quickly. So this is how quickly, the rate at which position changes, how quickly position changes. So if Miss Wu is walking, her position won't be changing as quickly as if she were running. The position changes more quickly the faster the speed is. And we actually can define the speed as the distance through which an object moves, that's the displacement, divided by a time interval. The unit that's used to measure speed, then, you can see, is it's going to be distance, units of distance, over units of time. We know the unit of distance is the meter, and the unit of time is seconds. So all we have to do is put those over each other, and that's the unit for speed. So the unit for speed is the meter per second, where per means division or over. We typically write this as m/s for meter per second. Let's check to see if you understand the definition of speed. The question is, what is Miss Wu's speed? So watch this video, take notice of the distance and the time, and all you got to do is just put distance over time and you'll have her speed. See if you can figure it out. Should mention, I'm expecting you to not use a calculator for this, so just round off the times. So instead of saying 1.835, you can just say 2 seconds. Just estimate it. See what you get for speed. In order to find Miss Wu's speed, we need to know her displacement, the distance she's traveled, and we need to know how much time it took to cover that distance. Well, we just watched this video in the last slide, and we found that her displacement was 2 meters. That was taking her final position, 3, subtracted by her initial position, 1, to get 2 meters. But what was the change in time? So notice that she hits the 3 meters at about 4 seconds. 4 seconds, and she begins at 1 meter at about 2 seconds. So from 2 seconds to 4 seconds is a change of 2 seconds. Now we're just going to write this out using symbols. The formula is going to be v for speed equals change in position, displacement, over the change in time. We already found the displacement, it was 2 meters, and we know the change in time was 2 seconds. Dividing these two quantities, 2 divided by 2 gives us 1, and meters divided by seconds is the meter per second. So Miss Wu's speed is 1 meter per second. Now this is her average speed. It's the average speed from this interval from 2 seconds to 4 seconds. This was her average speed. She might have been slowing down or speeding up a little bit within that interval, but this calculation is just finding the average over that interval. Here's a hypothetical test question that could be asked on what is speed. This would be a free response question. The question is, who has the greater speed? This is Miss Wu, she's walking, and this is Mr. Bhattacharya, and he's running. The important thing here is justify your answer. So I'm going to press play on these videos, and I want to make sure that you say who has the greater speed, but you don't just say Miss Wu, or you don't just say Mr. Bhattacharya. You need to justify your answer. Give a reason based on the physics definition of speed. Give me a reason why you chose who you chose. So who has the greater speed? Is it Miss Wu or is it Mr. Bhattacharya? Notice the times are still up there, the time it took them to travel across the screen. So who had the greater speed? Think about it and don't forget to justify your answer. When we justify our answers in physics, there are always two methods that you can use to justify your answer. Regardless of which method we choose, you're going to need to know two things. You're going to need to know Miss Wu's displacement and her change in time, and you're going to need to know Mr. Bhattacharya's displacement and his change in time. So let's go ahead and figure out what those were. So Miss Wu, she traveled from one end of the hallway, from 0 to the other end of the hallway at 5, which means her displacement was 5 minus 0. Her displacement was 5 meters. And the time it took, assuming that the video started at 0, which I believe it did, I don't see it, I just see the final time here. We're going to assume it started at 0, which means that there would be 6 seconds for her to reach the other end of the hallway. Mr. Bhattacharya, similar analysis would give us the same hallway, 5 meters, and the time of less than 1 second, so about 1 second to make it across the hallway. So notice that this information tells us who had the greater speed, because speed is distance over time, which means if Miss Wu and Mr. Bhattacharya traveled the same distance, the person whose speed is greater is the person whose position is changing more quickly. They both had the same change in position. Who did it more quickly was Mr. Bhattacharya, because it took him less time. So if I were taking this test, I would write this as my justification. I would say Mr. Bhattacharya had more speed because it took him less time to cover the same distance as Miss Wu. In other words, his position changed more quickly. He had more speed. Now this type of analysis, this is called a qualitative analysis. We're not actually performing any calculations. So we're just analyzing the qualitative aspects, the qualities of the problem. If we actually want to get in there and perform a calculation, that would be called a quantitative analysis because we're actually dealing with the quantities. And the way we do that is by using our formula. So let's go ahead and actually calculate the speeds and definitively prove that Miss Wu's velocity was less than Mr. Bhattacharya's. So the formula for average velocity is the change in position over the change in time. So we have a 5 meter change in distance and a 6 second change in time. If you do this, you get 0.83 meters per second for Miss Wu's velocity. And Mr. Bhattacharya's average velocity over that 5 meters is the same formula, his change in position of 5, his time of 1 second, and we get a speed of 5 meters per second. So now you can very clearly see, without any question, Mr. Bhattacharya was faster. His speed was almost 5 times greater than Miss Wu's. Often you will find that doing the calculations is much easier than trying to explain out using words and logic your answer. But the important thing is to do whatever you feel more comfortable with. If you want to answer using logical sentences, go ahead. If you want to use mathematical calculations, go ahead. Whatever way will get you to the answer, I'm happy. Now you may have heard me say interchange the word speed and velocity, and I need to be more careful about this because speed and velocity are not the same thing. Because you see, the velocity of an object is its speed and also the direction. So velocity is more specific. It's measuring more things than speed is. Speed is just measuring how fast, but velocity is measuring how fast and in which direction. So to make sure you understand this, I want you to think about this question. How can the driver of a car measure his or her speed? So imagine you're driving in a car. What can you do? What device can you use to measure your speed? I'll let you think about it. See if you remember what it's called. For a driver to measure speed, you'd need one of these. And this is called a speedometer or a speedometer. To measure velocity, we would need to not only measure the speed, but also the object's direction of motion. So how could a driver of a car measure his or her velocity? What devices would you need to measure velocity? So velocity can be measured using a speedometer to measure the speed and a compass to measure the direction. So it's not enough to just know the speed. You can't just use a speedometer and say my velocity. No, you need to know the direction. You need to have a compass and a speedometer if you want to measure an object's velocity. Please understand the difference between velocity and speed. It's a very subtle difference, but it's extremely important to understand. Velocity includes direction, and speed does not. Some final questions to ponder to check your understanding of speed and velocity. Here they are. Can two cars moving with the same speed collide? So I want you to imagine two cars driving down the road and they have the same speed. Can you envision a scenario where those cars would be able to collide with each other? Can two cars moving with the same speed collide? At first glance, you might say, no, they wouldn't be able to collide because they're going the same speed. Like if I'm driving on the freeway and the car in front of me is going the same speed that I'm going, there's no way we could crash into each other. But realize that speed doesn't include direction. If I say they have the same speed, they could be headed for a head-on collision at the same speed. So yes, two cars moving at the same speed could collide. An example of that would be a head-on collision, or any point where the cars cross paths. If they cross paths at the same speed, they can crash with each other. Let's ask this same question, but change one word. Can two cars moving with the same velocity collide? Velocity does include information about direction. Two cars that have the same velocity have the same speed and are traveling in the same direction. So unlike the case where they have the same speed, two cars at the same velocity can never collide because these cars would be moving the same direction. Their paths would be parallel. They could never touch. These cars could not collide with each other. So once again, please realize it's important to understand the difference between speed and velocity. The difference between speed and velocity can be the difference between life and death, a car crash and not a car crash. So there it is, you guys. That's PHYZR number 4. Hope you all have a wonderful day. This has been Mr. Keppel, and I'll see you in class.